Yeah, so I'm going to talk about stateless Ethereum. There's several aspects of it. I'm going to focus on Vertical Tree because that's what I'm working on. There's more aspects. There's state expiry. There's the portal network. There will be other talks about that afterwards. So I start with a big list of changes. We're just going to skim over them. But the main idea of vertical trees is that you replace hashes with polynomial commitments. It's the same principle, but the idea is that you can open a polynomial commitment, so you can get some information about the source data without actually revealing the data. And what we do, how do we use this? We start. We build stateless blocks, so we put blocks, we put a proof and a pre and a post state in the block. So you no longer need to keep the state locally on your machine. You just receive it along with the block, you execute it, you verify it's correct, you move on to the next block. And there's a lot of, I would say, practical changes that also get introduced. In order to, some of them are just to reduce the size of the proof. So for example, we look for a much wider tree, which means it's going to be much more shallow. And so the proof ends up being smaller. Everything gets merged into the same tree. We switch to 32-byte keys, and I'll get to the gas changes in a minute. So the proof, why do we talk about vertical proofs? Suppose you have a state and you want to prove the red rectangle. In a Merkle environment, you just need to pass every sibling because you need the whole pre-image to get the hash and to verify. In vertical proof, because you get some information, you can get some information about the pre-image, you just pass the information along the path. So in short, this is why you want to use vertical proofs. Block creation. So what happens? You start with the pre-state. So when you produce a block, you start with the pre-state. You figure out, executing all the transactions, what are the leaves that are going to change and what are the paths to those leaves. And then you just generate a proof, like a vertical proof, and you also get the keys. And then you add them to the block. So at the bottom of the block, you add the keys and the values and the vertical proof. And then, at the bottom of the header. And then, of course, you have the transaction list. And from that, when you receive that block, what you do is you rebuild the tree. And so the dashed rectangles are not available to the verifier. But it doesn't matter. All the information you need is in the solid line rectangles. And so basically you just maintain a key value store, and when you do this, you just update it. You update the tree. You do not need the other data. The block that has been given to you made sure that you would not need those other values. If you do, then that's an invalid block. And once you updated all those values, what you do is you calculate the root commitment. So it's no longer the root hash, it's the root commitment. And you just verify that it's the same as the one passed in the block. The way the keys were changed, so you switch to 32-byte keys. And what we do is we group keys we group values by groups of 256 leaves. And each account has its components, so the nonce, the balance, everything, represented by one leaf. And each value is available at one given offset. So for example, the first offset is the version, the account version, then you have the nonce, you have things like this. Then a bit later, you have the code, and then you have the storage data. So you know which slot you have, which code chunk you have. You hash it using a Peterson hash. It's like a hash, but a bit more sophisticated and easier to translate into ZK snarks. And then you have this, you take the offset, like the last byte of the offset verbatim, and you can index into that group. And that gives a tree structure that is a bit scary at first, but it's quite simple once you understand the basic principle. So what you have is, because the tree is very shallow, you have a high and very wide, you have a high branching factor. So the depth, the estimated depth for mainnet would be a depth of 4. So that means the first 4 bytes of the key would be would correspond to a branching, and after that, the rest of the stem for the following bytes until the last byte, you would have basically that you would be the only key with this prefix. So it would be very wasteful to insert internal nodes. So there are extension nodes only at the bottom of the tree. It makes no sense to have extension nodes inside the tree because, like I said, there's a high branching factor, so you will never need an extension node in what's called the stem tree. The part of the tree with only internal nodes or branch nodes, and then you have this kind of finicky problem. All values are represented by field elements, and those field elements are 253 bits. So if you want to store a 32-byte value, that's 256, you miss 3 bits. So what you have to do, you have to split it. You're laughing. You have to split it into 2 sub-elements of 16 bytes. And so you find yourself with having 512 values instead of 256. Well, it's still 256 value, but divided into each. So you need to have some kind of subtree. So you have 2 subtree called C1 and C2, which are effectively it's like an internal node, but it's at this level. It's a bit surprising at first when you know the previous tree, but you get used to it after a while. So just going back to the first slide, I wanted to go back to the gas change. You have, instead of because you're no longer storing data in the database, or at least you don't have to, what you do is you no longer charge, you no longer pay gas for storing data in the database. That's no longer the problem. What you do is you compete for block space. So when you access one of those groups that I was talking about, you have to add more elements to the proof. So you find yourself having to pay some gas to to add those elements to the proof if you're doing that for the first time. Once it's been added, so once you pay the gas cost once, you don't need to pay again because it's been the evil has been done. You added something to the proof. You bloated the block, so you no longer need to pay because you already paid for block space. And then every time you access a leaf for the first time, you also pay some gas because you add it to the list of key values. Right, so what is the current state? We have 3 library implementation. There's one in Rust, there's one in Python, and there's one in Go. We have 1.5 client implementation, so we have Geth with a modified version, and there's also Nethermind that hasn't really. We have 3 consensus bugs, so they haven't completely joined the testnet, but it's there. We're getting close, and there's a testnet if you want to go play with it. It's I've been told it's unpronounceable, so it's pronounced Condrieu. That's if you need. So what are we going to discuss this afternoon? The open problems. The transition. The transition is a bit of a. It's a problem that existed before we were talking about vertical trees. We were already mentioning that for the binary trees. So initially, the hope was to do some kind of state expiry scheme. I'm still hoping we can do that, but it needs more definition, more defining. There's still the old ID EIP 2584 of overlay tree. So you just add a new tree. You add a read-write tree. You make the Merkle tree read-only. You only write to that tree, and then you slowly, block by block, you convert. You remove some of the data from the Merkle tree, and you insert it into the vertical tree. And then it's an idea that has been suggested to me yesterday by Ed from Arbitrum. So this is not, I don't think it's going to be useful for L1, but in L2 they will also need to adapt to whatever the L1 is doing. And they were thinking of doing some kind of interactive proof, what they would do. So what they do when they have a fault proof in Arbitrum. So they would do some kind of, the client would propose a Verkle tree route, and if someone disagree, they can just make a claim and have an interactive game where they figure out where in the tree something was wrong. That means effectively that your reorg is based on an interactive game. I don't think that's gonna fly for L1, but for L2 it could make sense. Then there's the problem of stateless sync. The idea is simple. It's one of the big advantages of stateless. Because you receive the state in the block, you can just accumulate the data if you want to save it. And then you can go backwards in the block chain to get all the leaves that were not overwritten. Looks simple in theory. In practice, I'd love to discuss that this afternoon. There's the issue of address space extensions. So I don't think it has any champion at the moment. There was some proposal in the past with the Epsilon team who talked about the bridge contract. That was, I think because we're switching from 20-byte addresses to 32-byte addresses, some investigation should be done, but so far no one does that. And the last problem is data availability, and there's Piper's going to make a talk about this. That's it for the overview. Thank you, and check out the.